Assalamualaikum warahmatullahi wabarakatuh. My name is Adam Al-Hazi bin Abdul Aziz and my metric number is J24A1122, and today my group will be present about the observation under the SEM, also known as scanning electron microscope, and the comparison between ductile failure and brittle failure, the relationship between physical appearance and the properties of the samples. This is my group members. Introduction. The way a material breaks depends on its structure. By studying the fracture surface, we can identify whether the failure is ductile or brittle. Scanning electron microscope SEM is used to observe the surface clearly. Ductile failure shows rough surface with dimples because the material deformed before breaking. Brittle failure shows smooth and flat surface because it breaks suddenly without much deformation. These differences help us understand the material properties and behavior. Objectives: to analyze the microstructural features of material fractures during SEM results, to distinguish between ductile and brittle failure modes based on their characteristic fracture appearance. Third, to relate the observed physical fracture features to the mechanical properties of the material samples. And last but not least, to understand how the microstructure influences the material behavior under stress and guides material selection for engineering application.
Background of Scanning Electron Microscope SEM. Scanning Electron Microscope or SEM is an instrument used to observe the surface of materials at very high magnification by using an electron beam instead of visible light, as in an optical microscope. Because electrons have a much shorter wavelength than light, SEM produces clearer, more detailed, and higher resolution image. In this study, SEM is used in fractography to identify the type of material failure by examining the fracture surface. Uh, Through SEM image, we can distinguish whether the material experienced ductile failure or brittle failure and relate the fracture surface features to the material's mechanical properties.
Working mechanism of SEM. Number one, generation of electron beam. An electron gun at the top of the scanning electron microscope produces a beam of electrons. Number two, acceleration of electrons and focusing of electron beams. The electrons are accelerated by high voltage 1 to 30 kilovolt and focused using condenser and objective lenses. Number three, the raster scanning process. Scanning coils have moved the electron beam across the sample surface in a rectangular pattern. Number four, detection of signals. When the beam hits the sample, it interacts with atoms and produces signals. Last but not least, image generation. The signals are converted into electrical signals and displayed as a magnified image micrograph on the screen. Importance of SEM in fractography. Number one, failure topography identification. It allows researchers to distinguish between the dimpled surface resulting from microvoids in ductile fracture from the smooth and bright cleavage planes of the grain seen in brittle fracture. Number two, relationship between the structure and the properties of the material. SEM aids in establishing the relationship between the structure of the crack and the mechanical properties of the material, for example, toughness, ductility, and yield strength by means of images that show the nature of the cracks within the grains and along the grain boundaries. There are two types of failures, ductile failure and brittle failure. Ductile failure. Characteristics. Presence of dimples, rough and fibrous surface, significant plastic deformation, high energy absorption. Examples we got examples we have low carbon steel and aluminum alloy. Brittle failure. Characteristics: cleavage facets, river patterns, smooth and flat surface, minimal plastic deformation, and low energy absorption. Example we have glass, ceramics, and cast iron.
This table summarizes the difference between ductile and brittle failure. Ductile fractures show rough surface and dimple and absorb a large amount of energy before failure. In contrast, brittle fracture has smooth surface with cleavable space and absorb very little energy. Therefore, ductile materials are generally safer in engineering applications because they provide warning through deformation before failure occurs.
Observation of the SEM result. First, crack failure. Essentially a fracture of or separation in the material that grows under stress until it breaks. In ductile materials, crack often develop slowly, with stretching and deforming around the crack before it snaps. In brittle material, it tends to form cracks rapidly, leading to sudden failure without significant deformation. Second, cup and cone failure. In ductile material, when it breaks under tension, where the fracture surface often looks like a cup and cone, the material stretching and necking before breaking. Observation of the SEM result. Third, porous surface refers to the tiny hole or voids that appear on a fracture surface due to trapped gases during manufacturing. In ductile materials, these pores may form a microvolt that grow and link together before it fracture. In brittle material, porous surface exist but tend to be less prominent. Next, broken surface failure refers to the actual area where the material has separated into pieces during failure. In ductile material, surface usually rough and fibrous, showing sign of plastic deformation and energy absorption before breaking. In brittle material, the surface is typically smooth and shiny, reflecting a, reflecting a letting a rapid crack grow with little deformation. Observation of the SEM result. Fifth, the middle surface failure refer to the central portion of the fracture surface where the crack propagation is most visible. In ductile material, the middle surface may show signs of necking and microvolt coalescence. In brittle materials, it often displays cleavage, plane, or intergranular fracture patterns. 6. Broken and unbroken surface failure refer to the part of the material that remain intact around the fracture. In ductile material, the unbroken surface may show significant stretching and deformation, where indicating the material's ability to absorb energy before failure. In brittle material, the unbroken surface remains unchanged until the crack suddenly passes through.
Discussion of the results. Based on the SEM observation, several fracture surface characteristics were identified. First, cracks initiated and propagated until the material fractured. The sample also showed a cup and cone fracture, which is the main characteristic of ductile failure. This indicates that the material underwent significant plastic deformation before fracturing. In addition, the porous surface revealed the formation of microvoids during the fracture process. We continue. The rough and fibrous fracture surface further confirms that the material absorbed a high amount of energy before failure. The middle section of the fracture surface shows the crack propagation process, while the unbroken surface still exhibits signs of stretching. Overall, the SEM results demonstrate that fracture surface observations can be used to identify the type of material failure and relate it to mechanical properties such as ductility, toughness, and energy absorption capacity.
In conclusion, SEN observation successful in tigues before ductile and brittle failure modes. Ductile fracture a hip, dimple, and raw surface due to significant plastic deformation, while brittle fractures show cleaved face and smooth surface with minimal deformation. These fracture features are closely related to the mechanical properties of the material, such as toughness and ductility. Therefore, SEM is a valuable tool for analyzing material failure and supporting material selection in engineering application.
That's all from me. Thank you.